Okay, so chapter 13, we're talking about the language of probability distributions. So there are two types of probability distributions that we will deal with. We have the discrete probability distribution that we're going to learn about in year 11 and the continuous probability distribution that you'll learn about in year 12. Do you remember what those words mean, discrete and continuous? Discrete, anyone know what discrete means?
Like an exact measurement.
Whole numbers, correct. And continuous, a continuous scale, like measuring someone's height, for example. You could measure to the nearest meter, nearest centimetre, nearest millimetre, whatever. However accurate you can get that scale, you could continue to be more accurate with the measurement that you're given, right? So it's a continuous scale. So we're only focusing on the discrete probability distributions. If the sample space of an experiment can be written down in some order or listed, and the possible outcomes or values are numeric, then the possible outcomes together with their probabilities are called discrete probability distribution. So for example, if you toss 3 coins and the number of tails is recorded, the probability distribution can be seen below. It is called a discrete probability distribution because the values are numeric and can be listed. So the table there says we're listing the number of tails that we get when we throw those 3 coins. We could get no tail, 1 tail, 2 tail, or 3 tails. And underneath here we have the probability of obtaining each of those. And we did look about how to get those numbers in one of our previous exercises. We had a question on that, but we'll be looking at that again as well. So some notation in there. It says random experiments means throwing 3 coins into a bucket is a random experiment because there is more than one possible outcome. That's why it's a random experiment. Deterministic experiments means throwing 3 coins into a bucket and counting the number of coins is a deterministic experiment because 3 is the only possible outcome. Okay, so you're saying, I'm counting how many coins are in there. A random variable is usually denoted by a capital letter such as X. So you'll see up here in our table, we have probability with a capital X. That capital X is standing for the random variable. It is the result of running a random experiment. It can be numerical or categorical. Categorical data can be written using a probability distribution. Consider the words population by continent in 2016. We will deal with mainly numerical data. Okay, but this is an example of one that's not numerical data. So we've got our data in here. When we're talking about the population, we're actually listing the countries. So Asia, Africa, Europe, they're continents. They are not numerical. They're categorical data, okay? But the population that we're getting from that would be a numerical measurement coming out of that, okay? Uniform probability distributions. A discrete or categorical probability distribution is called uniform if the probabilities of all of the values are the same. Okay, so maybe keep that, I'm highlighting that word uniform. If all the probabilities come out the same, that would be the word that you would use to describe it. That is, the values are equally likely possible outcomes and the sample space is a uniform sample space. What is a list? Any finite set can be listed. The whole numbers and the integers do not form finite sets but can be listed. So for example, our numbers, as long as I'll give you kind of an ending point, we can list those numbers off. And we have some negative numbers in there as well. The real numbers in an interval such as 0 to 1 cannot be listed, because if I'm using the word real numbers, that means all of a sudden I'm on a continuous scale, because I could have any decimal numbers in between 0 and 1. So that is not a possibility here. We're only dealing with the discrete numbers. Okay? Continuous probability distributions. In a continuous probability distribution, the sample space is typically a closed interval, such as between 0 and 100 on the real number plane, on the number line. The sample space is therefore infinite and cannot be listed. Okay, so again, because we can have all the many, many decimals in between there, cannot have a finite list of numbers there. And we'll cover that concept in year 12, not for now. So what do we need to do today? Let's have a look at our examples. A dice is thrown. Write out the probability distribution for the number shown on the die and the graph for its distribution. So a distribution table that we're going to be drawing up has 2 rows. The first row is going to be our x, which is the outcomes that we can get when we roll a dice. So for a standard dice, that's the numbers 1, 2, 3, 4, 5, and 6. Then the second row is going to be the probability. Now, probability of capital X, remembering that the capital X stands for the random variable, and the little equals little x stands for the observed variable or the observed value that you get when you do that experiment. So I might observe when I roll the dice a 1, 2, 3, 4, 5, or 6, and it depends on which one I get. So the probability of rolling a 1 as my observed value is a 1 out of 6 chance. Probability of getting a 2 is also 1 out of 6. We know on a dice everything is equally likely, and they're all going to be a 1 out of 6 chance. Thank you. Okay, so there is our probability distribution written in a table. We are also asked to draw a graph of that distribution, which is pretty basic because there is only one value there. Our x-axis is obviously going to be for x, our variable. And we have the numbers 1, 2, 3, 4, 5, and 6. And our vertical axis is going to stand for our probability. So probability of capital X equals little x. And all of our probabilities were equal to 1/6. So just pick a spot on there, which is going to be 1/6. And then above each one of those, we're going to have a dot. Okay, they're dots because it doesn't join together. It doesn't go in between the 4 and the 5, for example. They only exist at the whole numbers. Okay, so that is our uniform distribution because they are all the exact same value, no variance. That's the word we're going to be using later on in this topic. No variance in those probabilities at all. Okay, so that is it. We've done the table, we've done the graph. Let's have a look at question 2. Mark is a determined person. He has decided to keep tossing a coin until it shows heads. Mark is counting how many times he tosses the coin. What is the probability distribution for this experiment? So that's the table, okay? We want to fill in one of those tables for this experiment. The trouble is, we don't know how many tosses of the coin he's going to have to do. Sorry. So let's start with just one toss. Let's get an idea of what's going on here. If he tosses the coin once, we are interested in the number of heads, right? So the probability that he gets one head on that first toss is a half. Got a 50-50 chance. Let's say it takes 2 tosses. Oop. So if it's going to take him 2 tosses, it means that he would have got a tail first, otherwise it would have ended after 1. All right, tail, then a head for the second toss. The probability of that is going to be a half times a half, which is a quarter. What about 3 tosses? So that means he would have to get tail, tail, and only on the third toss would he get a head. And you can see a bit of a pattern appearing here. That's going to be a half for a tail, half for another tail, and half for a head. It ends up as 1/8. So let's just do one more for good measure. 4 tosses would be tail, 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 and then finally a head. Instead of doing half times a half times a half times a half, let's now write that as half to the power of 4. Because if I did 5 tosses, it'd be to the power of 5. And you get the idea. That would be equal to 1/16 as well. So we could continue in that pattern. We want to write that, however, in our distribution little table here. So x, and the numbers on the top here are representing the number of tosses that it takes before you get a head. So 1 toss, 2, 3, 4, and then we're going to have dot, 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 because we're going to have to try and generalize this to go n times. N is the variable that we usually use for indicating for a unknown number of tosses. So for 1, our probability was a half. For 2, it was a quarter. For 3, it was 1/8. For 4, it was 1/16. Dot, dot, dot. For n, what is it going to be?
1 over n to the power.
It's going to be 1/2 all to the power of n. Another way to write that, 1 to the power of n is just 1 and 2 to the power of n on the bottom. Just a slightly more simplified way to write it. Okay, so that would be a probability distribution to represent that experiment. That's actually 13A, okay, and there will be some questions in there. We weren't asked to draw a graph of it, just the table. Yeah, but we are also going to go on with the next one.